Welcome back. Topic 4. Research-oriented conduction. A. Some conduction research topics. Conduction research is still very active currently. For example, there are researches on reducing contact resistance between metals, or research on heat conduction in complex geometries, like this fin with triangular perforation, or research on thermal stress due to quick heating or cooling localized in semiconductor, or research on macroscale or nanoscale heat transport in biomechanical or electrical cooling systems. Research also includes the methods to study conduction in terms of experimental methods, numerical methods, and analytical methods. B. We will use the example of two-dimensional steady conduction to show analytical and a numerical method. First, our system is a plane wall where one wall is held at higher temperature while other three faces are at a lower temperature. Second, the governing equation for this 2D steady conduction is represented in equation 1, and it is subjected to 4 boundary conditions. Third, analytical solution for this problem can be obtained for temperature, which is infinite summation of orthogonal functions like sine and hyperbolic functions. Fourth, this is the temperature contour with the solid lines represent constant temperature. If you draw the heat flux, which is perpendicular to the constant temperature line, the conduction is in the x direction as well as in the y direction. C. Solution strategy. Example of 2D steady conduction. First, the issue we have been facing is that even for a simple 2D steady conduction, the governing equation still imposes great mathematical challenge to obtain the solution for temperature. Then the question is, what is our strategy to resolve this issue? Well, we have to turn to advanced analytical solution and numerical solution. For analytical solution, it requires a strong background in the theory of orthogonal function, such as Fourier series, Bessel function, and it involves a complex series. Due to this nature, analytical solutions are not always possible to obtain, except for simple geometry and linear thermal boundary conditions. From research point of view, there are extensive studies of analytical techniques to solve PDE, for example, separation of variable, similarity method, Laplace transform method. If analytical solution is not available, we have to turn to numerical solution. It is obtained using very high-speed computer. The numerical solution is useful when the geometry of the object of interest is very irregular or the boundary conditions are very non-linear. There are many numerical methods in the research domain. For example, finite element, finite volume, and finite difference methods. D. Separation of variable method and a demonstration of analytical solution. First, our goal is to get analytical solution for this 2D steady conduction governed by the second order PDE in equation 1 on this physical system. Second, we assume a form of solution for this PDE, which is product function x and y. Third, substitute equation 2 into equation 1 to generate equation 3. The PDE becomes ODE. Fourth, equation 3 divides through by product xy to yield equation 4. In equation 4, left equals right only there equals to the same constant, which is set as lambda. Fifth, equation 4 can generate two ODEs for x function and y function. The solution of x equation is in the form of equation 6.1, where b and c are constants can be obtained through the two thermal boundary conditions in extraction. And the solution of y equation is in the form of equation 6.2, where d and e are constants that can be obtained from two thermal boundary conditions in the y direction. E is exponential function. This is sine cosine function. Finally, plug in the equation 6.1 and equation 6.2 back to equation 2 to yield the analytical solution for temperature. And then next, if we want, we can get the heat rate equation. E, finite difference method and a demonstration of a numerical solution. First, this is the second order PDE subjected to 4 boundary conditions to describe the two-dimensional steady conduction in this physical system. Second, the numerical method idea is that 1. we use a mesh network to represent this physical system where the mesh network identifies discrete points and uses an MN notation to designate their location. Finally, the temperature at each discrete point, is to be determined. 2. We use numerical method like a finite difference method to obtain the derivatives for temperature at each mesh discrete point like Mn. For example, temperature first derivative in the x direction and in the y direction is represented by temperature at two different points. However, the second derivative for temperature in the x direction and y direction is represent temperature at three different points. 3. Plug in equation 3.1 and 3.2 back to equation 1 to yield equation 4. Next, make the mesh size dot x equal to mesh size dot y. Then equation 4 becomes equation 5. If we know the temperature at this 4 point, we can obtain the temperature at point Mn. So 1, 2, 3, 4. Unfortunately, we have the mesh network has n mesh point. Therefore, there are n finite difference equations for n unknown temperature at those points, which is represented in matrix equation 6, where A is coefficient matrix n by n, T is the solution vector we're looking for, C is right-hand side vector of constants. Finally, if we solve this algebraic equations, we obtain the unknown variable temperature at those discrete mesh points. F. Thermal conductivity K. When the thermal conductivity K is first introduced, it is in the Fourier's law. It is used to measure the capacity of a material to conduct heat. This is a table, and the first column is material, second column is thermal conductivity value, the third column is some comment. If the K value is high, the material is heat conductor. Otherwise, it is heat insulator. Second, thermal conductivity K is slightly temperature dependent. If you look at this diagram, temperature, thermal conductivity, different materials, K most decreases for increasing temperature for the range from 100 to 4,000 Kelvin, except a few like stainless steel. K values increased with increased temperature. Third, thermal conductivity K can be a constant. We have run many times into it. Most metals, like copper, aluminum, silver, are isotropic, meaning their K value is constant. Fourth, thermal conductivity can be a vector. It indicates material thermal conductivity in three perpendicular directions, like R, theta, and Z, is different. Therefore, the material is called orthotropic. For example, wood is an orthotropic material. It conducts heat better along the grain than across it. So the thermal conductivity of the wood is a vector. Fifth, thermal conductivity of our general material could be a tensor, second order tensor. This nature of the thermal conductivity might be related to conduction mechanism, which is the transfer of heat by macroscopic collisions of particles like molecules and atoms, and movement of electrons within like a metal body. Therefore, the thermal conductivity of the materials is heavily influenced by material chemical compositions like impurities and its molecular structures like grain sizes. Research on thermal conductivity make efforts in two different directions. One is to find materials with really high thermal conductivity, which can extract waste heat very quickly, such as in most semiconductor electronics, including cell phone. Pay attention to the boron matrix, has really high thermal conductivity. The other direction of effort is to find material with really low thermal conductivity. In the past, there's a research finding the material CPS. This is a image of microstructure of this CPS material. The scale is 50 μm. And this diagram represented the thermal performance of CPS. This is the particle size in the unit of μm. This is thermal conductivity. By checking the thermal conductivity in the vertical direction is extremely small compared to the thermal conductive value in the horizontal direction. Therefore, this CPS is a great candidate for fire resistance material. At this point, we covered chapter 2, 3, 4, advanced conduction. This is the beautiful summary and outcomes about the concept, the variable, the scales, and the equation. And this ends of chapter 2, 3, 4.